presenter, Sagarika, is coming to us from Georgia Tech. Sagarika has worked this summer with Professor REU's group in condensed matter experiment. The topics therein being twisted graphene bilayers that are created in novel ways to create moire lattices that do really cool physics, but how do we make them? And why are they so cool? And that's all that we're going to be talking about, I think, today. Let's welcome Sagarika.
Okay. Hi, everyone. My name is Sagarika, and I am a rising sophomore at Georgia Tech. And today I want to talk to you about my work in expanding Twistronics wafer scale 2D films. So first, I'm going to walk you through some background information and the motivation for my research, which will be interspersed with some of the preliminary work that I did, and then I'll move on to my main work and the results from that, and then I'll conclude with the significance of that work and how I plan to expand on it in the future. So the field of 2D materials research really began with the successful isolation of monolayer graphene from bulk graphite, and that was done with Scotch tape exfoliation, which I'll get more into later. And then another major breakthrough came with stacking layers of 2D materials on top of each other. And those interfaces of the materials give you new and exciting properties. Twistronics is a sort of variation on that, where you focus on the angle between the two materials that you're stacking. And by changing the angle, you can change the properties that you see. And then something that evolves sort of separately but in parallel to that is a process called thin film deposition, which is where you can actually grow your 2D materials from the bottom up. What I want to focus on are the last two here, Twistronics and thin film deposition. And I want to try and answer the question, how can you scale up Twistronics research and applications using samples grown with thin film deposition? So first I'm going to walk you through Twistronics at its current scale, and then I'm going to get at the answer to that question. So on the left here, you can see two monolayer graphene lattices stacked on top of each other with that twist angle of 1.1 degrees. And you can kind of see the moire superlattice that has a much larger periodicity. And so that magic angle twisted bilayer graphene exhibits superconductivity and correlated insulating states, neither of which are present in regular graphene and come directly as a result of that moire superlattice. The other exciting thing about those properties is that they're highly tunable. So as you can see in those graphs, by changing the electron density in your sample, you can actually change what you see. So you can see why it'd be really cool to be able to scale that up in research and see all of those properties on a much larger sample. So that's all great, but how do you actually fabricate samples of twisted bilayer graphene? Let's start with twisted bilayer graphene at that smaller scale. So this is where I started my summer, Scotch tape exfoliation. You start with an initial peel from the bulk graphite mother tape, which you can see there on the left, and then you keep thinning that down using successive layers of tape to get thinner and thinner samples. And you want to keep your flakes as large as possible by using a small angle to peel and going very slowly so that you're being very gentle on your flakes and you're not tearing them. You're left with your graphene flakes on your silicon dioxide substrate. And when you look at your chips under an optical microscope, you can see flakes just like this one. This is in 50x under the microscope. So exfoliation is still widely used to obtain 2D materials, and the principles of this will show up later when I talk about how we actually work to expand to those larger films. Okay. So when you're actually fabricating twisted bilayer graphene, you start with a flake of monolayer graphene, and then you go and pick up half of it, and then you make your twist. In this case, it's 1.1 degrees. It's kind of hard to see, but you pick up the rest of the flake after that. So in practice, we start with a thick HBN or hexagonal boron nitride flake, and that gives us a nice bottom surface for our stack, which I will show in a minute. So in order to start off our stack, we start with a glass slide with a PDMS dome on it, and then we have a piece of tape with a small circular cutout, and that has our PPC film, which is both PDMS and PPC are polymers. Then you stick your PPC film over your PDMS dome, so when you flip your glass side over it, you have your PPC film over your PDMS dome, which serves as a cushion. Okay. And this will help us pick up our flakes when we actually do our stack. So yeah, these are images from a stack that I made of twisted bilayer graphene. It was actually at 1.1 degrees, so that magic angle. On the left here, you can see me picking up the thick HBN flake, and those rings are just that PPC film. And then on the right, you can see that flake of graphene. It's actually the same one that I used for that animation on the previous slide. and the one before that. I really like this flake.
It's a good flake.
Yeah, it's a great flake. So here, it's a little hard to see, but on the left, we're lowering our HBN down onto the top half of that flake. And then on the right, you can see the bottom half of that flake that's still left behind. It's that part that's outlined in black. The part that's like...
The South American part.
Sure, yeah. The southern hemisphere of the flake. But yeah, so the top half got picked up when we did that pickup on the left, and the bottom half is left there, and then this is after we rotated the stage by 1.1 degrees. So now on our left, we're aligning our HBN with the bottom half of that flake, and then we picked it up, which I didn't put a picture of because it looks the same as the first pickup. And then on the right, you can see the final stack, which has been flipped and placed on a silicon dioxide chip. So since we stacked in the order HBN, graphene 1, graphene 2, top to bottom, and then we flipped, we now have graphene 2, graphene 1, HBN, and then our chip. And then you can also see the PPC film in orange there. So now you know how you can make twisted bilayer graphene, but what can you actually use it for? Well, you can use it for a lot, actually. From superconducting electronics and quantum circuits to highly sensitive detectors, even neuromorphic computing, which is just like a computational style that mimics the function and structure of a human brain. But all of these applications rely on having large, uniform samples of twisted bilayer graphene in order to scale up. A uniform twist angle and large area allow consistent device performance in those quantum circuits, and then having a larger area increases your detector sensitivity, and you need many identical twisted bilayer graphene-based components in order to build neuromorphic arrays or logic components. But we're stuck with exfoliated graphene samples that are smaller than cells. So how do you scale up from there? Well, remember how I mentioned thin film deposition earlier? Molecular beam epitaxy, or MBE, is a method of thin film deposition that's used in both fundamental research and in applications. Done under ultra-high vacuum to give you clean and pure samples. So MBE allows for the growth of wafer-scale films, and it fits exactly what we're looking for. To actually do MBE growth, you have your substrate face down in a chamber, and then you have a bunch of other chambers that contain the materials that you want to deposit on that substrate. You evaporate them up onto the substrate where they react, and they form your film. This gives you a much larger surface of your 2D material to work with. You go from something that's not even visible to your naked eye to something that can be up to the size of my hand. So when you do MBE growth, you want to pick a substrate that matches the lattice structure of what you're trying to grow. Think of it like dropping marbles on a smooth table versus one with divots. If you drop them on a smooth table, they're just going to go everywhere. But if you drop them on a table with divots, they'll fall into those. That comes with a bit of a downside though. You now have an interaction between the substrate that you grew on and your grown material. It's become a lot more difficult to separate them. Okay, so let's review what we know so far. We have exfoliation, which is simple and gives us samples that we can easily manipulate and stack, but they're stuck at these tiny sizes. And we have MBE, which has much larger samples, but it's a lot harder to manipulate them. So ideally, we want something that will combine the wafer scale of MBE films with the ease of manipulation of exfoliated flakes. Luckily, in this paper from a team at Ohio State University, they demonstrated this method for transferring MBE films that results in minimal damage to the film itself. This process starts by spin coating the grown substrate in PCL film, which is just a polymer, and then they attach a PDMS stamp with thermal release tape onto that, and then they use a roller to slowly peel the film and everything on top of it off of the substrate. So the PDMS stamp here acts as a cushion, and you can see from figure B to D that they go from having a very rough-looking peel onto one that is still not quite perfect, but has a lot less of those defects. And then using the roller, we can get a really small angle between the substrate and the film as we peel off, and that's much less likely to lead to tearing and wrinkles. You can see you have like a near perfect film in F there when they use that method. You can also see how this action is relatively similar to that Scotch tape exfoliation we talked about earlier, with the small angle and the slow peel. So then they align the stamp with their target substrate and place it down, increasing the temperature to be able to lift off that thermal release tape, and then remove the PCL to leave the film on the desired substrate. So figure B and C show before the transfer, and E and F show after, and you can see how there's barely any added defects before and after the process. You can also see on the scale of that grown film that it's about 5 millimeters by 5 millimeters, and it's very clearly visible just with your eyes. Okay, so what we want to do is we want to take this process and we want to automate it. so that it becomes a lot more consistent and reproducible. And there's a lot of things that we looked at when we were thinking about what are we actually looking for this machine to do in practice. So for our machine, we want it to be motorized and to be able to move very slowly. That gives you fine control over like how quickly you're peeling off your sample and like how gently you're actually going. We want to be able to easily load in samples so that we can use this for many different films. We want to be able to adjust the pressure that we're applying to our sample like you would do if you were just doing it manually to be able to move that roller. And you want to capture that rotational and translational motion of the roller over the sample as you peel it off. So with these like design ideas in mind, we went through a lot of iterations in SolidWorks designing different versions of this machine, and we ended up landing on this one. So you can see here that we have this base motorized, so that way we can control that horizontal movement of our sample. We have these springs here and the ceiling, which can be lowered down so that we can adjust the force that we're applying down on through this roller onto our sample. And then we also have, when you want to load it in, you can just lift it up and either move this out of the way, or you can lock it in that higher up position and then load in your sample, and then you're ready to go. And then we also hooked it up to an Arduino so that we have some nice control over the actual motion of our motor. Okay, so now I'm gonna run a quick demo, and hopefully it works. So I have this control panel for the speed of our motor, and I don't have an actual sample on there, but I did put tape on it, so it should peel off the tape. Let's see. I'll keep that aside. So while that runs, I'm gonna walk through the rest of the presentation and we can see whether or not it works.
You can hear it trying to work.
Yeah, it tries a lot of stuff.
Keeps going.
Yeah, it's going. Okay. Okay. Back to the presentation. Okay. So, now that we have the machine, what can you actually do with it? This machine can allow for the dry transfer of any MBE grown material, allowing us to study clean samples without having to deal with that substrate interaction. It also enables us to fabricate devices. Oh, did it snap?
Something made a sound.
It's fine, probably. It also enables us to, that glass slide was broken when I put it in there, so it might be, I swear, I broke it yesterday. It also enables us to fabricate devices and heterostructures with any of the materials that we grow. So not only can we address the scale concerns of twisted bilayer graphene applications that I mentioned earlier, like quantum circuits and neuromorphic computing, but we can also focus on industrial commercial applications of many different MBE grown materials. So we can even use this machine to help us get better exfoliation, since like I talked about earlier, it has the same principles. We're looking for that small angle, slow peel. So what's next then? Well, one thing that we notice is that while we do see a consistently small peeling angle, which is all that we need if our sample substrate is really glued onto the glass slide, it's not just the downward force that controls that peeling angle. There's also the torque of the wheel being actually pressed forward as we move our sample, and I have some visuals to demonstrate what I mean by that. So here is the peeling angle that we get if we just run it currently. And you can see that it is small, but it's not necessarily following the curvature of the actual roller.
Oh yeah.
So in this video, you can see that if you apply force, that tape sort of peels up to actually match where the roller is. It's not, there's not that like gap where the angle is forming. It fits perfectly to the curvature. And so in order to get our films to peel following that design, is it good? Oh, you know, I think I'm going backwards. That might be why.
Wait, why would it matter?
So when you have your tape stuck on one side, you want to go in the direction so that it actually peels off. Otherwise, you're just going I probably should check that before I started.
Can leave it going.
You can do negative one.
That speed actually controls when you have your stepper motor, that controls basically the delay between of your square pulse. So if you make it negative, I think it's gonna not be happy about that. Okay. So we need to think about how we're going to apply that torque moving forward. And then the most important thing obviously is actually running it with MBE grown films. And then once we have those peeled films ready, fabricating an actual twisted bilayer graphene stack and comparing it to those exfoliation fabricated stacks like the one that I showed you earlier. And then we also want to look at using our machine inside a glove box in order to keep our samples as clean as possible. I would like to thank Dr. Zhu for all his guidance and help over the course of this project, and Kelvin, Priya, and Laxmini for teaching me how to exfoliate and stack, and then Chris and Braden for helping me actually assemble the final machine and put all of the moving parts together. Thank you. I'll just let that go during
Got a
questions.
couple questions, Jordan?
So in the first part of the presentation where you described creating the perfect angle for the moire pattern on the twisted layer of graphene, how exactly did you go about making that 1.1 degree angle?
So on our, I wish I had a picture of it, but for our stacking stage, the picture, or the stage that it's, our chip is actually sitting on, has a motor that can control the rotation of it. So, and that has a very high precision. So once we pick up the first flake, we rotate, or the first half of the flake, you rotate that stage by 1.1 degrees, and then you'll realign like I showed in that picture before, where you're trying to match where your HBN is and where that first flake of graphene falls on it to where your second flake of graphene is, and then you'll lower down and pick it up.
Thank you.
Alan?
I noticed on the pictures of the graphene flakes,
Yes.
they looked very irregular. Do you know if it's ever, is it ever done to cut them to be a regular shape, or does that not matter?
I would assume when you're at monolayer scale, they're probably pretty fragile. To be cutting them into specific shapes.
You probably want to preserve as much of the sample space as you possibly can to get as much area that you can look at.
Makes sense.
Because the next step is building devices on top of that, right?
So after you build a device,
Oh,
you
yeah.
can do some
How does it work
engineering.
with How well does it work with flakes?
That's cool.
Yeah. So full transparency, I got it moving 2 days ago.
Hey.
So
That's great.
I haven't been able to actually put a mother tape under it and see if it actually peels off well. Also, yeah, I think that place where I cracked the slide is, if I pull that down, it's peeling. Unfortunately, it's broken. So.
Yeah, but it still looks pretty cool. It's still doing what it's supposed to do. All right, awesome job, everybody.
Oh no, the table. It's broken.
All right, Patrick.